In this video, we're going to look at the final part of the earthworks, which is preparing the subgrade. Subgrade is generally described as being the top 1 meter of the formation. The road is built on top of the subgrade, so the material to the left and right of it is not part of the subgrade, it's just part of the formation. If the subgrade deforms or fails, then the whole road will fail. This means that the subgrade needs to meet specified strength requirements, specified bearing capacities. It also needs to be shaped the same shape as the road above. One reason for this is that any subsurface water will flow away from the load-bearing part of the road. Ponded water will weaken the subgrade soil, especially if it is a clay or a silt, and increases the risks of failure. Another reason is that for having the subgrade the same shape as the road is so that the subbase and base course layers, which are laid above, are consistent thickness, which makes them easier to lay, compact, and shape. The requirements for the subgrade are set out in sections 10 and 11 of TNZF1. It is worth reading this section in both the specification and the notes, as there are a number of requirements pertaining to the subgrade. Some of the most important are: soil with the highest bearing capacity is to be used in the subgrade, even if it involves extra time and cost, as we discussed in a previous video. The subgrade is to be laid as a continuous layer over both cut and fill areas. This means that the subgrade area of a cutting needs to be undercut below the formation level, and the fill needs to be brought up to the level below the formation level as shown in the bottom diagram. So the earthworks would look like this. The subgrade then needs to be laid in one layer. The maximum layer thickness for the top 400 millimeters of the subgrade is 135 millimeters, while the layers below can be no more than 200 millimeters thick. These thinner layers are more likely to be properly compacted. The top of the subgrade will experience the highest pressures in surface, so they need to be well compacted. Even with the best soil available on site, the soil may still be too soft to support the loads that it will need to carry, or it might be too sensitive to water, which means that it suffers significant loss of strength when wetted. The road formation can be constructed to allow for weaker soil, but this would require significant cost and extra thick road pavement. Therefore, the designer may decide to make the surface soil stronger using stabilisation. Subgrade stabilisation involves mixing lime or cement into the top layer of the subgrade soil. The additional water sets off a chemical reaction in the mix that eventually results in it solidifying into a hardened mass. This is similar to the chemical reactions that occur when you mix concrete. The resulting material is much harder and stronger than the original soil. It is more stable, which means it is less likely to be affected by water. Lime stabilisation involves the addition of burnt or hydrated lime to the soil. It works for most clayey soils, although you do need to test it to make sure that the chemical, the lime, is actually compatible with the minerals in the clay. Some fine soils have minerals that react with the lime and so it doesn't work properly. Cement stabilisation has Portland cement added to the soil. This is used for silty soils and coarse soils. Other parts of the road may also be stabilised. For example, the pavement material may also have lime or cement added to make it stronger. However, in this module, we will only look at subgrade stabilisation. Stabilisation process typically involves this following process. The lime or cement is laid on the subgrade surface from a spreader truck. Water is sprayed from a water cart onto the lime or cement to start the chemical process. The lime or cement is mixed into the soil surface using a rotary hoe. The surface is then compacted and shaped with rollers and graders. This is usually done in one process, as the surface needs to be compacted and shaped to its final levels and shape before the soil mix sets into a hard layer. This photo shows a lime stabilisation process in action. The lime has already been laid and hydrated. You can see it's the white material on the road. The white machine is a rotary hoe which is mixing the lime into the underlying soil. You can see that the material behind the rotary hoe is a mix of the lime and the soil. The compactor behind the rotary hoe is compacting the lime soil mix. A grader came along after and shaped the surface. The compaction and shaping needs to happen at the same time as the lime is laid. The compaction and shaping needs to happen at the same time as the lime is laid, as the hardened material is very hard to shape. So you have about a day or so to shape it up. Construction contract documents will also set out other requirements for earthworks, and the subgrade in particular. One of the most important properties of the subgrade is its bearing capacity. That is the pressure that the subgrade can carry without failing or deforming excessively. A common measure of the bearing capacity is the California Bearing Ratio, or CBR for short. There is a set procedure for the CBR test, so the test provides an accurate indication of how the material will behave under load. The designer would have determined the bearing capacity of the soil from the CBR lab tests and designed the road pavement assuming that the subgrade would meet that bearing capacity. Therefore, we need to check that the subgrade has the required bearing capacity during construction, so we do the CBR test in the field. Basically, the test consists of pushing a standard size plunger into the subgrade at a set rate. The force required to do this is measured and compared to the force required to penetrate a standard well-compacted base course material. The diagram in the slide shows the basic setup for a field test. The test requires a significant loading to be applied to the plunger, so the test apparatus is normally anchored under a vehicle. The load is applied to the plunger by a threaded rod on a collar, which is pushed down at a set rate as the collar is rotated. This causes the plunger to be driven into the subgrade at a constant rate. The resistance of the subgrade is measured by the proving ring. Stronger soils will provide more resistance, so the measured force would be higher. The CBR is the ratio of the force applied to the sample divided by the force required for the standard base course sample. So a CBR of 10 means that the force required was 10% of the force required for the standard base course material. A higher CBR value means a stronger layer. For example, soft clay would have a CBR of about 5 or lower. A sand would have a CBR of about 10. Lime stabilized material has a CBR of 25 to 30, and a base course should have a CBR above 80 and preferably pretty close to 100. Section 11 of TNZ-F1 provides the requirements for the subgrade surface shape, including the subgrade surface shall be firm, uniform and smooth. All points shall be within 30 millimeters from a 3 meter straight edge. This means if you lay a 3 meter long beam across the road, there will not be any points that vary by more than 30 millimeters, as shown in the diagram below. There should not be any ponding on the subgrade surface, which means no depressions. Ponded water can soak into the subgrade over time and weaken the soil. The deflection and other properties of the surface also need to be tested. Specification mentions the Beckman beam test, which measures the deflection of the surface under load. Basically, you park a truck with an 8.2 ton axle load on the surface, then measure how much the road surface rises when the truck moves away. So after the testing, we're ready to shape the road to its final shape. The shaping of the subgrade is done using a grader, which is a specialized piece of equipment designed to be able to shape the top of the surface down to an accuracy of a few millimeters. The grader moves along the subgrade, trimming off high areas and filling up low areas. The grader normally works with a steel roller or PTR, which compacts and tightens up the surface. Graders are wheel mounted to provide speed and because tracks would leave marks on the road. The diesel engine is mounted at the rear and powers the rear wheels. The front wheels are mounted on a long chassis, which provides a long lever arm that stops the front wheels from being lifted by the blade when it encounters high spots. This provides a stable platform for the blade mounted in between, allowing it to trim the surface down to a few millimeters accuracy. The blade, or mold board, is mounted on a turntable which allows it to be angled. Usually graders have a blade at the 20 to 30 degree angle to allow trimmed material to be side cast, that is, it moves along the blade to the edge of the blade. The operator normally tries to keep some soil travelling ahead of the blade to fill in any low points. The turntable, and therefore the blade, can also be tilted at an angle to the ground. This allows the grader to shape the ground as required. Most road subgrades are at 3 to 5% to allow water to drain away, and the grader has to provide that slope accurately. The blade can also be pitched forward and back to provide different sorts of cuts. These movements are all controlled by a hydraulic system. The grader can also be fitted with a GPS system, a global positioning system, that determines the exact location of the blade. Each GPS unit is continuously determining the blade's location in 3 dimensions and relaying that information to an onboard computer. The design of the earthworks is imported into the onboard computer, allowing it to compare the actual and specified ground levels and relaying that information to the operator. This allows the operator to adjust the controls to quickly and accurately produce the ground levels required by the design. Some systems automatically adjust the blade, leaving the operator to just drive the grader. The earthworks part of the road construction is complete once we've confirmed the surface shape and strength meet the requirements of the design. The next stage is the construction of the road pavement, which is the base course, subbase, and surfacing. This is covered in another module.